Hello everyone, I'm Alessandro Margara from Politecnico di Milano, and in this video, I will present the results of a collaboration between my research group and Infront Financial Technology on the definition of a realistic workload model to simulate high volumes financial data feeds for performance benchmarking. The main author of this work is Vladimir Zladojevic, who recently graduated in Politecnico. Special thanks goes to Sebastian, Alexander, and Mario, who provided the data we used in the work, introduced us to the domain of financial data analysis, and spent many hours in discussing problems and possible solutions with us. So the context of this work is the analysis of high volume streams of financial data, which is also the topic of this year's DEBS Grand Challenge. In practice, every decision in financial markets is driven by data. So companies working in the area need technologies that can process huge streams of events. So to give you an order of magnitude, Infront Financial Technology processes 40 billion events every day, with peaks of over 2 million events per second. And of course, not only high volume, but the event processing architecture also needs to analyze the streaming data and derive useful knowledge with low latency. Indeed, time may bring a significant advantage over competitors. As you certainly know, over the last decade or so, there has been a flourishing of software platforms to handle streaming data. Each platform comes with specific features, strengths, assumptions, and so on. So without even considering custom solutions, only looking at, for example, open source software platforms, there are already many possible ways to build very diverse data processing architectures. And this brings us to the problem we address in this research: how to systematically evaluate and compare various alternatives, and how to evaluate them in the specific context of financial market data. So first, a disclaimer: this is an ongoing project, so we still have to reach our final goal. And the final goal we want to achieve is a benchmarking tool to stress test event processing platforms and evaluate their performance in the domain of financial data processing. This would represent a realistic testbed to assess event processing platforms from a domain that is not represented in current benchmarking tools, and also a domain that presents pretty unique features. If you're interested, you can look at the paper, and also in some previous work, we discussed the differences in financial data with respect to other typical domains of event processing, say, for example, IoT. So that is the final goal we want to achieve. The focus of this specific work is to define a workload generator that captures the characteristics of financial market data. The requirements for this workload generator are that it is realistic, so it captures the key characteristics of the specific application domain. It is controllable, so it lets developers or users in general to change some parameters, then simulate different situations while preserving the fundamental aspects of financial market data. It is simple, so the parameter to tune the workload should be limited in number and easy to understand for experts in the domain, but not necessarily expert in event processing platforms and technologies. Finally, to be repeatable. So, for instance, to allow a comparison, a fair comparison of two platforms under the exact same conditions. We work under the assumption that the workload is realistic with respect to the load and load distribution, for example, the temporal distribution of event occurrences and the values of some attributes. But it does not necessarily reflect causal relations or other semantic relations in the payload. In other terms, we do not pretend to create an accurate model of the financial market and its trends. The approach we follow consists of 3 steps. First, we analyze different data sets made available by Infront to derive an abstract model of financial data streams. The model should be a representation that a simplified representation that preserves the key characteristics observed in the datasets. Second, we design a workload generator based on the model that includes a few easy to understand parameters to control the generation. And I stress here easy to understand. So simplicity and ease of use were key requirements for Infront. So we discussed them many times during our work. Third, we evaluate the quality of our model with respect to a different dataset, which is the one used in the DEBS 2022 Grand Challenge. The dataset was released when we were finalizing the work. So currently, we have only a qualitative evaluation, and we are studying suitable quantitative indicators currently. Here is an overview of the datasets we used for the analysis and evaluation of our work. For the analysis, we were provided with 3 different datasets represented in gray in this figure. In this figure, we show on the x-axis the coverage, so how many different data sources, instrument types, symbols, so somehow the heterogeneity of these datasets, and on the y-axis, the granularity, for example, the resolution in terms of time. So the 3 datasets we used for the analysis were rate statistics, represented as RSS in this figure. These are statistics about the rate per second coming from 6 different sources captured over 2 trading days. Then we have the global statistics, DRS, in this figure. These are daily statistics, so the granularity is lower. Daily statistics about sources, the type of financial instruments, and the symbols they publish. And then we have feed examples, CFS, here, which are over 300,000 event notifications published by 18 different sources. So high granularity and high diversity, high coverage. The DEBS 2022 Grand Challenge, GC22 here in black, represents a larger sample of event notifications, although they are not as heterogeneous as in the datasets we were provided. So as you can see here, due to the partial overlapping between the analysis datasets and the evaluation dataset, we think that the Grand Challenge is a good candidate to evaluate our proposal. So for the analysis of the datasets, we derive 4 key aspects for our model. First, exchange categorization. Exchanges are the sources of data. So one or more exchanges publish into a market data feed, which is analogous to an event stream. So exchanges are the sources of data that publish through streams or feeds. We immediately noticed that exchanges exhibit very different behaviors in terms of the data they produce, and in particular in terms of the instrument types they publish. Instrument types are like bonds or certificates or equities or funds or indices, just to name a few. We use the clustering algorithm to identify classes of similar exchanges. The datasets included 14 different instrument types, and we use them to build a 14 feature space, and we use a k-means clustering algorithm with different values of k, number of clusters. We then selected the smallest value of k, after which the solution does not improve any further, meaning that in terms of similarity of elements within each cluster, we did not improve the solution further. As a result, we obtained 12 classes of similar exchanges, and for each class, we derived the set of instruments that they produce. Some of them produce only 1 or 2 or very few types. And then for classes with more than one type, we compute the frequency of occurrence of each instrument type. Second, we derive a distribution for symbols. Symbols denote, for instance, a specific index, like the NASDAQ, Dow Jones, or a specific company, Microsoft, Apple, whatever. As you can imagine, symbols are highly skewed. For instance, many transactions involve a small number of very large companies, as you can imagine. We immediately noticed that trying to identify classes with common trends would be practically infeasible. It would add a lot of complexity to the model without really improving on precision. So we tried to fit the curve of symbols distributions, and we found that the distribution is what can be well approximated by a Pareto distribution. In our workload generator, we define n classes, each producing the same number of events. Then we distribute symbols to classes. The first one includes, so the first class includes few symbols that are very frequent, and then we increase the number of symbols and we decrease the frequency until the very last class which includes a lot of symbols that occur with very low frequency. So in practice, we noticed that for the data sets we had, we could achieve a very good approximation already with 4 classes. So you can think of it as having an extra large class of symbols, so symbols that are few symbols that are very frequent, down to the small class, where there are many symbols that they are very infrequent. Third aspect that we derive from our analysis is the temporal distribution of events. Event generation is not constant over time and follows trends that are both at a coarse and at a fine granularity level. So we use a 2-step approach to capture both. At a coarse granularity, we derive a typical daily pattern with the average rate computed every 10 minutes on the dataset. And you can see the pattern on the right of the slide. Okay, so there is an opening time and a closing time. There are 0 events before the opening and after the closing, and then there is a certain trend. At a fine granularity, the time distance between consecutive events follow an exponential distribution, where the average is obtained by the daily pattern, but within each window of 10 minutes in the daily pattern, there are significant differences in the trends. So there is an exponential distribution that models these differences. Finally, 4th aspect, we consider the set of attributes available and missing for each symbol. So for event representing or describing a given symbol. We look at each instrument type and each symbol, and we compute the probability that a given attribute is present. Notice that for each symbol, some attributes are always present and many attributes are always missing. In the datasets we had, attributes were encoded and we did not know their exact semantics, although we had some discussion with Infront. What we could derive was a set of template symbols that we could use in our workload generator. So we had these templates and the set of attributes and the probability that these attributes appear. We also tried many other different types of analysis, including more complex patterns, such as correlations between the presence of some values or the values of some attributes, but we could not find recurring patterns with high confidence. So that was the model. So then based on the model, step 2, we propose a workload generator that works as follows. We rely on a limited set of parameters shown on the left. There is a set of feeds, streams of events, with few associated features. The set of exchanges they include, the rate of event omissions, the latency of the communication channel with that feed. Okay, so recall that a feed is like a stream of data, a stream of events, and the exchanges are like the sources of events that publish through that stream. Then a small set of parameters is defined for each exchange that determines the opening time, the day length, the maximum rate to customize the daily curve, then the class of exchange among the 12 that we identified with our cluster analysis, then the set of symbols that we want to associate. Recall that the number of symbols and their relative frequency of occurrence is already defined by the class. So here we determine exactly the set of symbols that we associate to the exchange. Okay, so on the left you have the parameters that you can select. On the right you have an overview of the algorithm used in the workload generator. You don't have to read the details, but the basic idea is that we have a set of feeds and each feed has a set of associated exchanges, sources. For each exchange, we generate events using a compute event procedure that determines the content of the event. And then there is a submit event procedure that computes the delays and omission in event delivery. Finally, as I mentioned, we currently only have an initial qualitative evaluation based on the Grand Challenge public dataset. We report here one result on the left that appears to be similar but slightly different in the Grand Challenge dataset, which is the distribution of symbols, which is even more skewed in the Grand Challenge dataset than what we can derive and what we use in our model. Instead, on the right, the daily pattern of event notifications is followed by, with a good approximation, by all the exchanges in the Grand Challenge dataset. Here, on the right, you can see the Amsterdam NL exchange, but similar patterns are visible for all other exchanges. And this concludes my presentation. So I'm really looking forward to meet you in person, finally, and to discuss this research project with you at DEBS. So see you soon.